Alright, so we are going to cover momentum right now. So this plane has a mass and it will travel with a certain velocity. Momentum is equal to mass times velocity. So when we fly this plane and get it in the air, it will have a velocity that we can use to calculate for momentum. Another important thing that we must understand is impulse and what it has to do with momentum. Impulse can be described as the effect of a force acting over time. It is denoted as capital F multiplied by delta t, with delta t describing a change in time. Impulse and momentum come into play with the impulse-momentum theorem that describes how impulse is equal to a change in momentum. In short, the impulse experienced by an object is equal to a change in momentum. So to visualize this, we'll take a look at this plane. So let's go ahead and start the plane up. And we're going to turn off the engines. And it stops instantly on that tree. So when we see that it crashes, we're able to calculate using the impulse momentum theorem. So the impulse that the plane experiences is equal to the change in momentum. So when we see that the plane hits the ground and stops instantly, we can figure out how impulse, which is force multiplied by a change in time, is equal to a change in momentum. Alright, so we're now going to work on energy. Here we have a powered vehicle that will tow this smaller, unpowered vehicle along with a rope. In order to understand energy, we must first understand work. Work can be described as the force enacted on the body as long as the body undergoes displacement. So with this visualization here, we can see that with the use of the powered vehicle and the rope, work is being done on the smaller unpowered vehicle. So when work is done onto a system causing it to move, then we will see a change in its speed, which in turn changes its kinetic energy. This brings us to the work energy theorem, which describes how the work done by a net force on a particle equals the change in the particle's kinetic energy. So when we look at the car towing the unpowered vehicle at rest, we can figure out the work done on the system by subtracting the initial kinetic energy from the final kinetic energy. Alright, so we are now going to focus on oscillation, and the best method of teaching oscillation is through a pendulum. So the equation for a time period measured in seconds for a pendulum is 2 pi times the square root of L over G. G just being the force of gravity, and L being the distance from the center of suspension to the center of mass. And so we can visualize this here with this pendulum, because we can see that each center of mass is connected to a center of suspension with differing lengths, meaning that length is one of the primary factors that affect the time period of which a pendulum oscillates. And so that creates this pattern here. And so as you can see, the time it takes to go from left to right or right to left in one cycle is going to be different when we look at the differing lengths from the center of mass to the center of suspension.